Okay, so we are in chapter 4 of An Introduction to Statistical Learning, and we are on question 3 of the conceptual part. Here is the question, okay? And so in this question, well, in fact, I'll just read it verbatim. Okay, this problem relates to the QDA model, so quadratic discriminant analysis as opposed to linear discriminant analysis, which we addressed in question 2, in which the observations within each class are drawn from a normal distribution with a specific mean vector and a class-specific covariance matrix. We consider the simple case where P, or the number of parameters, or also the number of explanatory variables, equals 1, i.e. there is only one feature or one explanatory variable. So suppose that we have k classes, and that if an observation belongs to the kth class, then X becomes a one-dimensional normal distribution, where X is distributed, is that supposed to be X? I'm not sure, but a normal distribution with mean mu k and sigma k, or variance sigma squared k. Recall that the density function of a one-dimensional normal distribution is given here, and prove that in the case of a Bayes classifier, that the Bayes classifier is not linear. In fact, it's going to be quadratic. Okay, so let me just pause this for a second. Okay, so again, the quadratic discriminant analysis differs from the linear discriminant analysis here, or no, I'm sorry, here. Okay, so in linear discriminant analysis, which I'm going to scroll back up for, we have that the variance parameter is the same among all of the k classes. Okay, right. So here we just have sigma squared and no subscript. In other words, all of the classes share a similar or the same variance estimate. Okay. Now that changes in quadratic discriminant analysis because now we assume that each of the k classes may have its own separate estimate of the variance within that class. Okay, and so whereas the delta function for linear discriminant analysis, right, which we went over in number 2, was linear. Okay, and we say it's linear in X because so here we have the only X, and X is not raised to any power, right? So so in this case it's linear. Okay, so we're linear in X when we assume that all of the classes have the same variance function. Okay, well, what happens then when we don't assume that every function or every class has its own, when we don't assume that every class has the same variance, right, that the variances may change? Okay, how is that going to differ? All right, how's the delta function for QDA going to differ from that for LDA? Okay, so in order to do this, what we're going to do is we're going to follow the same steps as before when we were deriving the delta function for linear discriminant analysis, which you can look at that video. But instead of starting with one estimate for sigma squared, we're going to have an estimate for, we're going to have sigma squared subscript k, so that every class has its own variance. Okay, so that's what we're going to do. I'm not going to walk through. The steps here. You can follow that on your own time. But the important parts here is that we are carrying through sigma k. All right, the whole way through. All right, and so now at the end we have this big function here. Okay, and this is almost our delta function for QDA. All right. Now when we were doing LDA, in fact, let me scroll back up to the LDA derivation. We had this. This was our final. Step when we were taking the logarithm of f of k. Okay, and then to convert this to the delta function for linear discriminant analysis, we just simply went through and looked for all of the terms that depended on k somehow, right? So this first term has a k in there, and that shows up in the delta function. The second one does not have does not reference the kth class, right? So so to have this does not discriminate between one class or another, so we can discard it. Okay, and when we go here, we have a mu k, okay, and so that makes it in there, but the x squared over 2 sigma squared, that doesn't reference k, and so it's not in here, and so on and so forth, okay? Well, this function, okay, looks very, very similar to this function here. The only difference is that now our sigmas have a k on there. So now we follow that same rule. Whenever we have a k, we keep that term in our final function for our final delta function for QDA. And so then that turns into this, as opposed for linear discriminant analysis, this. Okay? And so now what we see is that now the discriminant or the delta function for QDA is quadratic in x. Why? Because I go to my x value and I go to the highest term and I see an x squared there, as well as an x to the 1 power here, right? But because we have an x squared, it is quadratic in x. Okay, so now we've done what we were supposed to do, which is to show that the discriminant function for QDA is quadratic. That's what this is implying. Okay, so now I'm going to keep going here. So that is the answer, but there's a couple of things that I want to do as well. So what about the boundary? What about the boundary function, or the decision boundary for LDA as well as for QDA? All right. So the book gives us the decision boundary for LDA, okay, and I'm just showing how to derive it here, okay. And basically the steps are, so I take the delta function for class A and the delta function for B, and the decision boundary is where these two things are equal to one another, okay. And so if you just go through, and solving for x, you get this term, right, or I'm sorry, you get this expression right here. Okay, so this is the x value at which class A and class B are equally probable. Okay, and if I make the assumption that the prior probabilities for class A and B are the same, well then this term, log of those two things, becomes 0, and so this whole term becomes 0, and that drops out, and we get this function. And this is the expression that's given in the book. Great. Okay. In fact, the book even gives a, well, we'll get there in a minute. Okay. So in other words, if I go to the x value, if I have an x and y axis, and I go to the x value where this is where I go to this value for x, then the two classes are equally probable. Okay? All right. Well, how might this change for, well, okay, one more thing. Notice that this is a linear function as well, okay? It's actually a constant, okay? It's a constant function. All right. So, I shouldn't have said linear. This is a constant, okay? And there's one solution to it. All right. But in quadratic discriminant analysis, we saw that the QDA is quadratic. Now, quadratic equations have two solutions. Okay, so what we're going to do is now we're going to solve for. We're going to solve for the x value or x values that represent the decision boundary for quadratic linear analysis. Okay. So this gets a little bit ugly and hairy, and so again, I'm not going to walk through it, but again, the first thing we do is we set two discriminant functions for QDA equal to one another, okay, which is what I've done here for class A and class B. And then I'm just going to take this whole right side and subtract it from the left side. So now I have this whole equation set to 0. And now I'm just simplifying until I get to this expression right here. And this is not pretty looking, but notice that what we have is we have a quadratic equation. We have an x squared followed by this, and this is just a constant, okay? Or we're treating it as a constant. We have x, and we have its constant here, its coefficient. So we have ax squared plus bx, and then all of this stuff is c set to 0. Okay, well, we know it. Well, there's a lot of ways to solve quadratic equations, but we can just plug this into the formula for quadratic functions, and we get out x, okay? Or we get out the x values that meet this requirement. So I'm not going to go through and plug all this out. This is just a big exercise in algebra, but that's how we would think about solving that. Okay, so finally, I did some playing around in Desmos, okay, and so you can check out my graph here, but I will just pull it up. Okay, let me zoom in here. Okay, so let's just get our bearings here. All right, so I'm starting. In fact, let me just get rid of these things. Okay, so first I have a normal distribution here. Okay, and we'll call this Group A or Class A. Okay, and then I have another distribution here, another normal distribution. And we'll call this B. Okay. Now, here I'm adjusting the parameters of these two distributions, right? So M, it stands for mean. So if I move this, I'm moving the mean of A. Okay. If I move MB, I'm moving the mean of B. And then I can adjust the standard deviations of them as well with SA and SB. So I'm just going to set those equal for right now. And then PA here, this is the prior probability for A. And then the prior probability for B is just 1 minus probability of A. So notice as I move probability of A up, nothing is happening on the graph. Well, you can't have that much more. Okay. So if I go to 0.9, well, then probability of B is 0.1. Okay. And similarly, if I go down to 0.1 for probability A, then it's 0.9 for B. Okay, but I'm going to set it to 0.5. Okay. So now remember, so let's look at linear discriminant analysis first. Okay, so I have my two normal distributions here. And so what we're trying to do with linear discriminant analysis is to find an x value that picks out where if data falls on one, if x falls on one side or the other of the line, then we should lump it in with one group or the other. Okay, so the first thing I'm going to do is I'm going to make the assumption that we have the same standard deviations, right? Because that's what linear discriminant analysis is assuming. And I'm also going to assume that the probabilities are the prior probabilities are equally likely, okay? And so now here I have my expression that we already derived for the boundary decision for linear discriminant analysis, okay? And here it is, it's the green line. And what we see is that it precisely intersects where the two curves are equal. Okay, so that's interesting. So there's our boundary condition under the assumption that the prior probabilities are equal. Now, let's say that I believe my prior probability for A is that it's more likely. Okay, that Class A happens more than Class B. Okay, so I'm going to adjust that a little bit. Maybe not that much. Okay, that much. Okay, now our line shifts to the left. Okay, so in other words, what is happening is that because I think that that A is more likely than B, okay, even though I have data that seems to line up more with B, right, because I'm closer to the big bump in B here, because I think A is more likely to begin with, I am taking X values that are encroaching into what I might call B's territory. Right, so hopefully that makes sense, okay? And similarly, if I make A less likely, okay, less likely than B, so now B is more likely, even though I have an X value that has pushed into A's territory, I'm saying that because B was more likely to begin with, even a value that falls just on this side of my decision boundary, I'm going to call Class B. Okay, so that's all interesting. All right. The other thing to notice is that when I have standard deviations that are the same between the two groups, okay, so when I have equal standard deviations between the two groups, which I do here, over on the left-hand side, these are my decision boundaries for quadratic discriminant analysis. Notice that these are undefined, okay? So that's interesting to note. So in other words, it's just interesting. Okay, so now what happens if I adjust my standard deviations a little bit, okay? So I'll just make them a little bit different. So notice that the normal distributions kind of become a little bit dissimilar. And now I have boundary condition, or decision boundaries for the quadratic discriminant analysis, okay? Now they don't show up here, and it's because the relationship portrayed on this graph and the decision boundaries are not very clear cut, and so you should play with this. But I can start to get them to show up as there's one of them as I don't want that much, as I start to play with the standard deviations of these guys. So anyway, you can play with it. I think this video is just about out of time, so I better go.